Before I introduce the complete binomial theorem, let's take a look at some of these examples, and this will lead us into the binomial theorem. Here we're expanding the square of a sum, and x plus y squared, that's x plus y times x plus y, and here we FOIL, and we obtain four terms. And of course, we can combine these two terms here because they have the same variable part. So that's why you see 2xy. But instead of looking at that final expression, I want to look at this expression here and notice that the quadratic terms, so these are quadratic terms. In these quadratic terms, if you look at each one of them, they have two blanks that you can fill with x's or y's. We can look at them as slots. And the first, you can put either x or y, and same with the second one. So you can have two x's, one x, or no x. Right? Two x's, one x, like in these two, and no x's. So these are the format. So I can say these slots can have two x's, one x, or no x. Let's take a look at the cubic expansion here. Three factors of x plus y. And the first two can be obtained by the previous example. And we FOIL that previous expression with x times x plus y. So it will be that entire expression times x, and then plus then that previous expression times y. So xx times x, xy times x, xy times x, and yy times x. And then the same expression again times y. And notice that each cubic term, we can look at them as a group of three slots, right? We can use all three slots for x's, or out of those three, we use two for x, and then the other will be for the y. We can use one x and the other two for y's, and no x's. So it can have three x's, two x's, one x, or no x. The binomial theorem will give us the number of like terms we have in these expressions. So here, for example, for the quadratic expansion here, we only have one term with x squared. So the binomial theorem will give us number 1 there. And the number of terms with x, one x and one y would be 2. So there are two terms like that. And there's only one term with two y's. So the binomial theorem will give us those numbers, those coefficients. In the cubic expansion here, we have only one term with three x's, and we have three terms with two x's. We have this one, there are two x's there, two x's, and two x's here. So if we combine the like terms, we'll have 1 x cubed, and then 3 terms with 2 x's and 1 y, 3 terms with 1 x's and 2 y's, and 1 term with 3 y's. The binomial theorem will give us those coefficients that you see here. Well, the question now is, how do we count the number of like terms in general? For example, if we have the expansion x plus y to the 9th power, for example, right? Well, then again, you will see several terms being added, and each term is a term of 9th degree, right? So you will have 9 slots. Each term will be a mix of x and y's, one more slot here. And so you could have all of the slots with X's, or all of the slots with Y's, or some of them with X's and some with Y's. So these slot, it will be a bunch of terms. In each term will have 9 blanks, right? 9 places you can put X's and Y's. So these ninth degree terms can have 9 X's or 8 X's or 7 X's, all the way down to no X's. How many of each type are there? Well, if we look at this expansion, how many terms with 9 X's do we have? We can look at again at each term having this format with 9 slots. And of those 9 slots, we are selecting some of them for the X's and some of them for the Y's. So the terms will have either 9 X's. In that case, we select 9 slots out of the 9, right, for the X's. Now this is a combination. We're selecting some of the slots for your X's, and this gives us a total of C 9 9. That's 1. If you compute that number, that will give 1. And then the next type of term would be a term with 8 X's. Again, we select 8 slots out of 9 for our X's. So those types of terms would be the terms that have 8 X's. And how many of those terms do we have? Well, we can count that by computing the combination. Out of those 9 slots that we have available, we're grabbing 8 of them for our X's. So this will give us the total number of those terms that we have in the expansion. And if you want to calculate that, that's according to the formula, this would be 9 factorial divided by 1 factorial times 8 factorial. And this would be 9. There would be 9 of those terms. And let's do one more here. There will be terms with 7 X's. That will be selecting 7 slots out of 9 for your X's. That would be C 9 7. And this goes all the way down to 1x and no x. You will select 1 slot out of 9 for your x, and that's out of 9 we select 1 slot. And finally, no x means that all of the slots will be used for the y's, right? Will be filled with y's. Or selecting 0 slots, right, out of 9 for your x's. And we can actually compute this as a combination 9, 0, and that's actually 1. So there we have the total number. When we do this expansion here of x plus y raised to the 9th power, we will have a lot of terms. Each term will be a term of 9th degree. Each term will have 9 blanks, and those blanks can either have x or y's. Some of them will have 9 x's. Yeah, in fact, only 1. Some of them will have 8 x's, and there are 9 of them. Some of them have 7 x's, and that will be this number of terms. And that's basically what the binomial theorem is saying. So we can simply write x plus y to the 9th power. that would be C 9 x to the ninth. Why is that? Because we have that number of terms of x to the ninth power. And we'll have C98 of terms with 8 x's. Now, if the term has 8 x's, that means it should have 1 y, right? Remember, each term has 9 slots. If 8 of them are filled with x's, then there's 1 filled with y's. And how many are there for that one? Well, there's C98 of them. And C97. There are that number of terms with 7 x's. If those terms have 7 x's, then each one of them has 2 y's. And this goes all the way down to 1 axis, so there's C91 terms with 1x. Well, if that term has 1x, and the term has to have 8 slots, right? 8 factors, then 8 of them must be the y's, must be reserved for y's. Finally, there's C90 terms with no x's. That means all of them are y's. And that's what the binomial theorem says. We can also write this as x plus y raised to 9. And instead of starting with the C99, we can actually do C90. And the idea is the same because if you look here, selecting 9 slots for your x's is the same as selecting 0 slots for the y's. So the number would be the same. So this is actually the same as C. Let me use a different color here. So this is the same as C90. And selecting 8 slots for your x's is the same as selecting 1 slot for the y's. So out of 9 slots, I'm selecting 1 for the y's. And here, selecting 7 slots for the x's is the same as selecting 2 slots for the y's. So this is a symmetry property that combination formulas have. This is C98, right? Selecting 1 slot for your x is the same as selecting 8 slots for the y's. And then finally, this is C99. So you can actually write this expansion as C91 x8 y and C92 x7 y2 C98 x y8 and C99 y9. So it's the same expansion. And then here is the binomial theorem. For every positive integer n, this expansion, x plus y to the nth power, is given by C n0 x n plus C n1 x n minus 1 y, right? Since we have n, each term will have n factors. All of them, if all of them are x's, then we have this number of them, which is 1. Combination of n, 0 is always 1. And the number of terms that will have n minus 1 factors of x and 1 factor of y would be this number. And we expand this all the way to C n, n minus 1, x, y, n minus 1. And here's the last one, Cn, n, yn. And that's what the binomial theorem says.